Hello, in this particular video we're going to have a look at one particular approach whereby we can get an AI control character to aim a projectile so that it arrives in a certain position. It's worthwhile, I suppose, pointing out that there's a wide collection of different algorithms and techniques within this area, all about aiming and firing, where you sort of want to determine a set of parameters that will enable you to launch a projectile so that it arrives in a particular target location. Or conversely, for a projectile that is flying through the air, to work out where it is likely to land, and then based on that information to decide if you need to move out of the way. But we'll have a look at one specific example. It's fairly illustrative, simple one, but it's illustrative of quite a few of the other techniques. So what we're assuming here is that, well, it really is mentioned that we want to give our AI control characters the ability to aim the projectiles, arrows, missiles, or whatever, or even footballs, whatever it is, so that they can get them to arrive in a certain position, or alternatively to work out if they're going to arrive near them. We will assume that we have a trajectory of motion for an object that is launched in a certain direction with a certain velocity, and then it is subject to a gravitational force. So in other words, if I were to throw a ball, that would be fine. I would launch it in a certain direction with a certain speed. After that, then we have gravity pulling it down. We're going to ignore things like air resistance. We're also going to ignore things like a rocket which imparts its own energy into the travel as well. So for throwing a ball or for firing an arrow, the equation of motion that describes where it is at a particular point is as shown on the screen. This actually is, maybe a little bit yuck, but actually it's fairly straightforward. So we have a P0, which is the initial position. So position at time is equal to t is equal to 0. So this is where I throw the ball from, effectively. If you look at the next position, has a number of terms here. We have d, which is a directional vector, so it's of unit length, and it points in the direction in which the projectile was thrown. We have sf, is the speed at which it was thrown. And those two combined, the direction and the speed, is basically the velocity. We're basically saying then that the velocity times the amount of time that has elapsed is one of the components of the position, and that makes sense. So that if I throw it at point p0, then after 1 second it's going to have moved a direction of sf, the speed, in the direction d that I have defined. So all we're doing is just simply defining that straight line motion. We're assuming that gravity is affecting this. Now gravity is an acceleration, so it has an incremental effect on the velocity, an incremental effect on the position, so it's a squared term. So it's a half times gravity times the amount of time that has elapsed squared. So over time it will be the gravitational element that will become dominant within this particular equation. Looking at that equation, you can sort of see it's quadratic in form. We'll get onto that in the next slide, but we have a t squared with a t and just some other number. So we're going to try to solve that. Gravity, in terms of the Earth at sea level, it's 9.81 meters per second downwards, or towards the core of the planet. That's gravitational attraction on Earth. Quite often within games, you use a different value. You pick a value so that it looks right whenever you're playing the game. You've got the right amount of gravitational speed dropping characters down. So you're free to tweak or change that as you wish. Now, for finding out where, if I were to throw a ball using this equation, where it's going to land, I need to solve that equation. And I'm going to solve it for a given floor height. So I'm not really interested in the x coordinate, or I can work that out, but what I want to solve it for is specifically just the y coordinate. Let me show you a little bit here. The equation on the previous slide, it is a quadratic equation. And the general form of any quadratic equation is, ax squared plus bx plus c is equal to 0. So we have a quadratic term. In our case it's time, t is the thing we're interested in. Any quadratic equation can be solved as shown in the particular box. So if we work out minus b plus or minus the square root of b squared minus 4ac over 2a, that will give us the solution to that particular algorithm. We can work out then what value of x, or t in our case, that we plug in will give us our target value. And for us, we're solving it, and if you look at the equation at the top, you see here that we've ignored the x terms. So for the direction, we're only interested in the y direction. For the gravity, is only the y component of the gravity. So we don't care about the x location at this point. We simply care about the height of it. And we're going to work out, or to solve the equation for a given height. Now, this might be 0, that represents the ground. If I'm higher up, then it will be whatever height I have. But that's what we're solving the thing for. So we're going to use the general form of solving the quadratic equation. When using this form, you'll either have 2 solutions, 1 solution, or 0 solutions. So if the b squared minus 4ac, if that's a negative number, we can't take the square root of that and get a real number, it's an imaginary number. So in this sense, we get 0 real solutions. What does that mean? So if we solve it for a given height, and it turns out that b squared minus 4ac is a negative value, it means that it never ever reaches that height. There's no way of solving it where it reaches that particular height. So you know, we've thrown something, it doesn't get as high as we're interested in the thing reaching. If we get 1 solution, so b squared minus 4ac is equal to 0, that means that it does reach that height once, just at the apex of the throw. So as it reaches up and goes to the top and then starts to come down, that's just where it touches that height. If we have 2 solutions, what this means is it reaches the height twice. So we throw in the ball, it'll reach the height once going up, and then reach the height a second time falling down. So it's really the descent one that we're interested in, the one where it's falling down is the particular value that we want to work out as to what time will it take for that second y value, the falling value, to arrive. If we know the time, we can then work out the precise x and y location. So you can do this in a piece of paper yourself. All we're doing is we're substituting into that particular quadratic form the equation that we have. We're getting 2 solutions, and I'll look up this particular form that we have on the screen. We're basically, you know, there's a 3-dimensional one here, the x, y, and the z. If you're doing a 2-dimensional game, obviously you drop the z component from it. This maintains gravity having both an x and a y coordinate. Often gravity is just simply in the y direction, if it's your traditional game. So it simplifies to the form shown on the bottom of the slide. But by solving that for a particular height, we can get the time, plugging it back in, we can then get the position at which the ball will hit our target location, or target height on the ground. There's various things we can solve it for. So we know where we want to, what height difference we want to do. Invariably, there's going to be some variables within this here. So if I'm throwing it, I can then vary maybe the direction in which I throw it. I can vary the speed at which I throw it. And depending upon the type of simulation, this will determine what it is able to vary. So if it's, for example, a bow and arrow, you can sort of assume that the initial speed at which it will be thrown won't change, but the direction could be changed. If it was something else, I was just throwing it, maybe I can control the direction, I can control how hard I throw it. But given that equation, we want to say that, okay, we know our particular position where it lands, or our target location we want it to land in, what value then do we put in that will enable us to try to get to that particular position. Doing this here, if you do get 2 solutions for it, they generally represent a couple of different arcs. So I could throw it sort of low and fast towards it. I could throw it higher up in the air. It takes a longer time to get it. Generally speaking, you pick the arc with the lowest time that reaches the point, unless you sort of think there can be things in the way where you may want to throw it up high. But you can solve it for either of these. Expressed as a fragment of code, we'd have the following thing. So calculate firing solution. Now it returns a vector with question mark here. So this is pseudocode. Basically it means that, yeah, most times if we can reach it, we'll return a vector, but sometimes if we can't reach the particular target location, we're going to have to return null to represent there is no way of reaching it. So we take in our starting point, we take in our target that we're trying to hit, we take in our gravity vector, and for this particular algorithm we're taking in the speed at which we throw it. So the variable that we have here, the thing that we are returning, is the direction in which it is going to be thrown, so that it leaves the start position and hits the target location. So we're doing a few things. We're working on our delta value in the A, the B and the C from the algorithm. Here we're using the dot product because we've got vectors with x and y component. Remember, dot products do simply the x components multiplied together and then added to those the y components multiplied together and the z components and so on, depending on the number of terms. That gives us our A, or B and our C. That's from the equation we had earlier on. We check to see, do we have any solutions? In other words, do we have a positive value we can get square root of? If we don't, it means we never reach that target location, no matter how we throw it. We'll return null. Other than that, we then calculate what the two values are. Now it's possible here that they could be exactly the same if we only have one solution, but we're just going to go ahead and calculate two of them because that's by far the most common outcome. So it's the same type of calculation. We're sort of doing adding the square root, in our case subtracting away the square root. You could write this in a more efficient way so you're not doing the same calculations twice. We have a bit here at the end then. This will give us two time values. And we do a few checks. We're also checking here to see, okay, that we have positive times. When we solve this, one of the solutions may be a negative value. It sort of represents that if we were to sort of throw it in the past, so if you like the inverse direction of travel, it would reach the target height. Now, mathematically it's sound, but it doesn't make any sense for us because we're considering time as moving forward within the game. So we do a check here. We pick, we ignore negative times. Beyond that, we pick the smallest positive time as the one that we are interested in, and then we return the particular direction for that value of t that we plug into it, and that's the direction in which we throw it. That will entail that the whatever it is will leave from the start position, pull down by gravity, and will hit the target position. So it's a reasonably compact piece of code. Key takeaway there, aiming fire solutions is a fairly big area. We showed you one example within this of a non-powered projectile, just an only thrown projectile that's subject to gravity, about how we can work out where it's going to land, and equivalent to that, then work out, okay, what angle do we throw things at to hit a target location, or if something's coming